Alright, in this video we're going to be talking on elimination reaction in alkyl halides. Now this video is a continuation on the last video I actually made, which was talking about substitution reaction in alkyl halide. That was giving us the mechanism on substitution reaction in alkyl halides and conditions in which substitution reaction occurs. Now this is like elimination reaction. Substitution, we know that means like displacing one and replacing it, mostly displacing the alkyl halide. Elimination means removal, that is removing the alkyl halide and another group to actually like form a different element. So that's what we're actually going to be talking about in this video. So now alkyl halide undergo elimination reaction to yield unsaturated hydrocarbons. Now this reaction occurs in two ways. That's something we need to know. Like just like substitution reaction that I gave you last time, the reaction occurs like in E1, that is elimination unimolecular, and E2, that's elimination bimolecular. Now I'm going to be talking about elimination unimolecular. So let's start with elimination unimolecular. Elimination unimolecular reaction mechanism E1. Now this mechanism is similar to substitution unimolecular reaction mechanism, but like the reason why I say it's similar is because of the first point I actually gave. That means both of them follow first order kinetics. That means the rate equation will be given by K in bracket raised to the power concentration and raised to the power 1. This is concentration of whatever we're using. But now still like substitution unimolecular reaction mechanism, like elimination unimolecular reaction mechanism also depends only on the concentration of the alkyl halide. That means the concentration of the nucleophile is not needed in this reaction mechanism. It's only the concentration of the alkyl halide. What I'm actually going to be talking about in this A1 mechanism is going to be similar to substitution SN1 reaction mechanism. The only major difference between this E1 and SN1 is the way, like, it's just elimination and substitution. That means the way the nucleophile will attack and all those stuff. That's just like the mechanism. That's the only difference. But other factors that affect SN1, they also affect E1. And another stuff that I can actually just put, E1 is mostly seen in tertiary alkyl halide, just like SN1 is mostly seen in tertiary alkyl halide. Now, hence the rate equation can be written as R is equal to K in bracket raised to the power concentration of the alkyl halide. If I may, let me just remove everything. So I said the rate equation will be equal to K. This is Rx. Now this is the rate equation of E1 reaction mechanism. If we followed my last video, that's on SN1 reaction mechanism, we find out that this is similar to the previous equation I gave on SN1 reaction mechanism. Now, another stuff that is similar. That's why if you understand SN1, you won't have any problem with E1 reaction mechanism. It is also a two-step reaction mechanism and it involves the formation of a carbocation intermediate. I gave you this point on my last videos. Now you can actually see it forms a carbocation intermediate. That carbocation intermediate is actually this. I'm actually going to come back to this equation. So now let's start. I said it's a two-step reaction mechanism. Now, we're going to be talking on the two steps involved. Now, let's start with the first step. Just like SN1, 2, homolytic fission of the alkyl halide. Now, this is the alkyl halide that we're giving here. Now, like you can see from what I said earlier, is a tertiary alkyl halide. This is a tertiary alkyl halide. Now, the first thing that involves is homolytic fission. That means this X group, the X that is the halide group, will actually leave. And that will make this, it will leave and take this electron with it. And that will make this carbon, that's the alpha carbon, that's the primary carbon. Let me just call it the alpha carbon. Primary carbon can actually confuse some people because of there are different types of alkyl halide, primary alkyl halide. So let me call it the alpha carbon. So this carbon here is the alpha carbon. Now this alpha carbon will end up becoming electron deficient because carbon is meant to have 4 bonds attached to it, and now one of the bonds have been taken away by the halide group. That means this bond, it has been taken away by the halide group and taken away by this X group. That will make this carbon electron deficient, and at the end of the day, this bond will no longer be there, so the carbon will have a positive charge, and that positive charge that the carbon will have is what forms the carbocation. That is a carbon cation, if I just call it that way. Now and this X group, that means this will take the positive charge. So this is the first step in the reaction mechanism. Now the next step in the reaction mechanism involves the loss of proton, in brackets hydrogen, from the beta carbon atom by the alkyl halide to the nucleophile. This is the major difference between SN1 and E2 and E1. I mean, the only major difference is in the second reaction mechanism step, and that's what I'm talking about. Normally in SN1, what actually happens is a substitution. That means this nucleophile will actually come in SN1. The nucleophile will come and bond here and end up leading to the formation of a different product, just like alcohol and so on. But now the nucleophile won't end up coming to bond here. What the nucleophile will actually do, it will deprotonate a hydrogen, to deprotonate a hydrogen, not from the alpha carbon. Note that it's going to deprotonate from the beta carbon. It can't deprotonate from the alpha carbon. It's going to deprotonate from the beta carbon, and the position is actually going to deprotonate is from this position. As we can see, is from this position, not that position I drew earlier. It's from this position. That is a position opposite to where, completely opposite, or what should I say? Just like that. I don't know what I should call this line now. I can't remember the name, but just put it like a cross, just a cross, like that. Like if the, like from what I showed you guys earlier, does this. Let me just erase everything. This is the position of the halide group. Now the hydrogen that's going to be deprotonated is from this position. It won't deprotonate from this position. That means the position that's parallel to it. It's actually deprotonate from this position to deprotonate. That's the only position you can deprotonate from. So it end up deprotonating from an opposite position, and that will end up leading to the formation of this. Now, this step is a slow step, as we can see from what I wrote here. Slow. It's a very slow reaction mechanism, but the next step that we're actually going to be talking about, that's this step. It occurs fast. When the nucleophile actually deprotonates the hydrogen, it leads to the formation of an alkene. An alkene, look at, there's a double bond here. It leads to the formation of a double bond alkene, and at the end of the day, NUH, whatever the nucleophile is, it will lead to function. If the nucleophile was OH minus, it will lead to function of water. If it's any different nucleophile, cyanide, all this stuff, it's function of different products. Now, note, the nucleophile deprotonates the beta carbon at its side opposite to the point of attachment of the halogen. I've made this point clear earlier when I was saying that it's going to deprotonate from this point. Don't mind my positioning of this. I just wanted to put my plus in a place that you actually notice it. This bond can actually be found here. Don't just, regardless of the position, I just wanted to make sure my positive charge is indicated. So that's what is just happening here. Now, since E1 involves the formation of a stable carbocation, it can thus be said that only alkyl halides that can form a stable carbocation can undergo elimination reaction by this mechanism. Like I said earlier, only alkyl halides. That's tertiary alkyl halide. Secondary can also undergo, but stable carbocation. We all know the reason why tertiary alkyl halides form a more stable carbocation than primary or than secondary, because tertiary alkyl halides, they have other alkyl groups attached to it. That is 3 other alkyl groups attached to it, and these alkyl groups are electron donating. So regardless of it missing that bond there, having a positive charge here, regardless of it missing that bond, it has 3 alkyl halides that will end up trying to stabilize the loss of electron there, because the alkyl group is the electron donating group, so it end up trying to stabilize that lost electron and to end up like forming a more stable ion than primary. Primary only has one. And one can't actually stabilize this positive charge well. So at the end of the day, that's why we see something like methyl ion is not stable. But if you look at something like third butyl ion, third butyl carbocation, it is stable, and that's what we're actually just talking about here. So therefore, A1 mostly occur in tertiary alkyl halide and do not occur in primary alkyl halide. The point I just talked about. Now, A1 reaction trend. This is just the trend of like how A1 can occur. That we can see now from tertiary it occurs greater, secondary less, and primary the least of all. Now, let me just give you an example. Now, this example, I'm going to be using third-butyl chloride. That's like the most simple form of a tertiary carbon or a tertiary alkyl halide that can give third-butyl chloride. So now this is my C. Let me just indicate all of this with R prime. And this is R prime. So now, then this is ending up becoming my Cl. Now this is my third butyl chloride, regardless of the R groups. That means different alkyl groups. Now, what did I tell you is the first step? I tell you the first step involves homolytic fission of the alkyl halide. That's this step here, homolytic fission of the alkyl halide, and that's what I'm actually going to be talking about now. Now, it's a very slow step, like I said earlier. It's slow, and what actually happens is this. Alkyl halide phase now, this R prime and this prime, and this has a positive charge, and this ends up getting a plus and a negative charge. Now, this is the first step of the reaction that I actually told you about. Now, the second step is still easy. Let's say our nucleophile is OH minus. This is our nucleophile, a Lewis base, OH minus. You can use any form of nucleophile, H2, NH3, as far as it has electron. I mean, it's electron donating, just use that. Now, the second step that I'm actually going to be talking about, that is this. What's that? That is the deprotonation of the beta carbon. Note the beta carbon, the deprotonation of the beta carbon by the nucleophile. Now, we all know this was what we had. Okay. Now we had this. These are R and these are R prime. These are R prime. Okay, let me just like give groups for this R prime and R prime because I need to get a beta carbon here, so it will be easier for you guys to know what I'm talking about in this deprotonation. I'm going to be changing this group. I'll not be changing all the groups, only this R prime group. I'm going to be changing and I'm going to involve a carbon in that group. So that's the only group. So let's say this R prime is equal to methyl CH3. That's what I'm actually going to be changing. The rest won't be changed. So let's start again. So I have my C, then this is my R, and this is my R prime, and this ends up becoming my C, then H, then H, then H again. Then this has a positive charge, like I gave you earlier. Now I said the second step, the nucleophile being NH3. Nucleophile being NH3, if I may change the position of this R prime and just indicate it here, so I may end up giving a better scenario. Let's say this is the point. This is the point where the halide group left. Let me make a different color. It's not important that you indicate this point that I'm actually doing. What I'm actually just trying to do is just to give you a rational example. This is the point where the halide group left. I'm just trying to show you where the deprotonation will occur. This is the point where the halide group left. So now my R prime can actually just come and stay here. Over here, R prime. This is the point of release of the halide group. Now, from this point, the nucleophile being OH, so nucleophile being OH minus, will actually come and deprotonate from this point. We can see this is the point of loss, or what should I say, this is the point of fission of the halide group. That's the X group. This is the point of fission, and now the nucleophile will come and deprotonate this. Let me use a different color to come and deprotonate this hydrogen, and at the end of the day, it will end up leading to the formation of this. So this end up becoming our C, then H. It will deprotonate it. Note, it won't take away this bond. this bond here, it won't take it away. It's that bond that will actually fall down and form our double bond. The nucleophile, like I said earlier, is an electron donor. It's a Lewis base. While Lewis base electron pair donors, it has an electron here. It's willing to share this electron. It's not looking for electron. It's willing to share an electron, and it's going to take away this hydrogen without thinking of taking the bond or taking the electrons that are in that line. So it will actually just go and share its own electron with this hydrogen, and this hydrogen's bond actually fall down here and form a double bond. So this is our double bond. This is the hydrogen bond. So let me change the color so we won't end up getting confused. So now this is the hydrogen bond. Now, so at the end of the day, this ends up becoming our hydrogen bond. This is our hydrogen bond. Now, let's continue with the structure that was actually talking about. Now, at the end of the day, our R groups come here. First one come here, and then our R prime comes here, and this is what we end up having. Now, as you can see from structure, that's just like what A1 is actually talking about. Don't be confused. This is just like an example. Now, I actually gave a structure here, so you can actually you can actually just look at this structure and you can actually just see what's happening in a planar way. What I'm just giving you is an example, and that's just all about E1 reaction mechanism. So now let's go to the next one, A2 reaction mechanism. Like A2, where I said it stands for is elimination bimolecular reaction mechanism. That's A2. Now, just like SN2, just note E1 is similar to SN1. E2 is similar to SN2. The only difference is the reaction mechanism. One involves elimination, one involves substitution. So the steps I'm actually going to be giving you are just like the same. That's why I told you that you need to actually go back and watch my substitution reaction mechanism video before you can understand this one 100%, because then I introduce the topic and I'm actually just going deep into that right now. So now this follows the second order kinetics. The rate equation is given by this. Now, these are rate equation, just like SN1. So these are concentration, whatever the concentration we're dealing with, raised to the power 2. Now, just like SN1, the rate of the reaction depends on both the nucleophile and the alkyl halide, and hence it can be written as this. Now, don't be confused by this equation and this equation. Don't be confused by that. This is just like one concentration, but if we say this multiplied by this, let me just put a dot there. We put a dot there, it's still going to be giving us this answer. Don't be confused. What I'm just actually saying here is that the rate depends on both the nucleophile and the alkyl halide. Unlike E1, that the rate only depended on the alkyl halide, the nucleophile plays a part in it. And now, it's very similar to SN2, like I said earlier. It is a one-step reaction mechanism. The nucleophile deprotonates the beta carbon in the alkyl, and with nucleophile deprotonates the beta carbon in the alkyl halide, and at the same time the halide group leaves. That's just what I'm just talking about. They are leaving at the same time, and that's just what's happening. As this is deprotonating, this is leaving. It leads to the formation of a transition state. That's one is still leaving, one is still coming in. One is still living and one is still deprotonating since none is coming in. Now, this leads to the formation of a transition state in which the halide ion is still departing, and the deprotonation of the deprotonation by the nucleophile is still occurring, and that's just what's happening. Now, look at the structure I'm just giving. This is not a comprehensive structure. You can just say a CC. This is the alpha carbon, and this is the beta carbon. So don't be confused. That's the alpha and that's the beta carbon. Now, what did I say at first? The first step involves they occur at the same time, but let me just take it step by step. That is, at first, we can see from our dotted lines, that we can see that the alkyl, the halide group is still living. As the halide group is still living, the hydrogen is still being deprotonated by the nucleophile, and that's what is just happening. it forms a transition state in which one is still happening and the other is still happening, but it's just a one-step reaction mechanism. It's nothing hard about it, unlike the other one that it will lead to function of a carbocation first, then before the nucleophile can actually just come and deprotonate. This one, the nucleophile is deprotonating and the halide group is leaving, so it's still like the same thing that is happening. It must deprotonate from the opposite side of the beta carbon, like what is happening here, from the opposite side of the beta carbon that the halide group is leaving, and that will lead to the formation of an alkene. This is the alkene, and this is the halide ion, and this is the nucleophile, whatever it might be. If it's OH, it's a lead function of water and different products. Now let me just give an example, a very simple example. Let's ethyl chloride, so we can have something like C, this and C. Let's say C and this. So at the end of the day, this is our H. This is our Cl, and this is a H. So now I said it's occurring at the same time. So I'm going to be changing this line into a dotted line. So let me change it to a dotted line so we won't end up becoming confused. So now these are dotted line 1, 2, 3, and now it's going to be deprotonating from the opposite side. So now the nucleophile being OH minus will actually be coming here, and what it will be doing to be deprotonating this hydrogen, and at the end of the day we end up forming the product that we saw earlier, CC. That's the alkane, and water Cl minus. Those are just our product that we end up forming, and that's just all about this. Now, thank you for watching this video. Please like and subscribe to my channel. Remember, this is a continuation on what I actually talked about last time, and the next video I'm actually going to be talking about now is elimination reaction versus substitution reaction. I'm going to be talking about what happens, why a reaction will choose elimination, or a reaction will choose elimination or substitution, either one. What factors does elimination and substitution depends on, what must a scientist actually do in order to choose what the product you want to form, if you want to form an alkane or a substituted alkyl halide group. So that's what I'm actually going to be talking about. So just thank you for watching this. Goodbye.